Our final section that we're going to look at out of Chapter 10 is regression. When we are talking about regression, we're talking about a straight line to model the relationship between paired data, like the shoe prints and the heights that we looked at in the previous section. We'll work with this a little bit further and then look at a second set of data that gives us slightly more interesting results. But for now, let's start with what we mean by regression. We're going to find an equation of a straight line that best fits the paired sample data. This is going to be similar to the equation of a straight line, y equals mx plus b. This best fitting straight line is called a regression line, and its equation is called the regression equation. It expresses a relationship between x, which is known as the independent variable, and y, which is the dependent variable. So you have y equals mx plus b. We're going to write that as y equals b0. So that's going to be the intercept coming first, and then the slope times x. In regression, this is the order in which we do that. We write the slope first and then b1x. So b sub 0 is the y-intercept and b1 is the slope. When we're talking about a population, we have those Greek letters again. So in this case, it's going to be beta. But when we're looking at a sample, we have beta is now b for the b0 for the y-intercept, b1 for the slope. And then the equation of the line is, as you just saw, b0 plus b1x. So we're going to have to figure out how it is that you calculate b0 and b1. Okay, we're going to be looking at samples of paired data. It's got to be random. We're going to do a visual examination with a scatter plot and see if there's any hope of a line being used to approximate the pattern. And then also we can use a visual examination to see if we can find any outliers. You got to pull those out. Those have an incredibly detrimental effect on the regression line. Here are the formulas for slope and the y-intercept, so b1 and b sub 0. You can see here that you have the R, correlation coefficient. And so we use equals correl, use that function in Excel. This is the standard deviation of the dependent variable. This is the standard deviation of the sample standard deviation of the independent variable. And for finding the y-intercept, we have y bar, which is the average of the y data, like what we have over here, and then minus b1, which we just calculated, times the average of the x data. So since we know how to find R with correl, we know how to find the sample standard deviations, and we know how to find the average. We're going to be able to figure out the slope and the intercept of the regression line. Okay. Here is that example that we looked at in section 10.2. We have the shoe print in centimeters and the height of males in centimeters as well. And we looked at this before, and the same requirements are going to be necessary in this section as well. You have to make sure that your data is a simple random sample. Got to look to see if the scatter plot gives you roughly a straight line and that there's no outliers. We looked at this data already. We looked at this data previously. I'm just using this as a simple example to help show how it is that we can construct a regression line. And so here are the equations, but I want to show you how it is that we come up with all of these numbers using Excel. So I think we'll go back to slide 5 here. And so to calculate the slope, we're going to need the correlation coefficient, the sample standard deviation of y and the sample standard deviation of x. So here we go. Come over here to Excel, and let's find the average of each of these. Here's the average of the shoe print. And I'm going to do the same thing for the heights of the males. And then we need to find the standard deviation. It's a sample standard deviation of the shoe prints. And we need to find the sample standard deviation of the heights as well. And let's go ahead and find the correlation coefficient for these guys equals COREL. Array 1 was the print, comma, array 2, close parentheses, bam. All right, so the equation for slope is equal to correlation coefficient times standard deviation of the y variable divided by standard deviation of the x variable. Hit enter. Boom. There you go. There's our slope. 1.73 is probably what we're going to round that to. And then the y-intercept. Let me say the y-intercept. That's going to be the average of our dependent variable. So we'll say equals the average height minus b1, which is the slope, times the average of the x variable. And you can see that right up here. We had b7, which is the average of the y variable, or the height, minus the slope times the average of our print size. And hit enter there. You get 125.4. So there's our slope. There's our y-intercept. If we jump back over here into this, we'll see that you get the same thing when you take correlation coefficient, the average y over the average x. You get 172.745. And then for the y-intercept, you get the 177.3 minus, you can see that's the equation we have right here, minus the slope, which is b1, times the average x value, it's 125.4. So what we have here is the slope and the intercept for the regression line. And when we put that into a scatter plot, this is a scatter plot. We saw something similar to this last class, and here's our regression equation. Here's the equation that describes a straight line best estimate for these points. Now, I hope that you're already thinking of this, but don't you remember that when we talked about these points and we did the correlation coefficient, remember we found out to be 0.591, and then we compared that to the value in table A6. I think you should remember that 0.591 was less than the critical value in table A6. So we found already that this is not a significant relationship between shoe print length and height. Let's cover a few things that we have to be on the lookout for. Use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. It doesn't look so good. There are some points that are way out at here, nowhere near this straight line. The second point says use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation between the two variables. This is what we did back in section 10.2. when we looked at 0.591 with a sample size of 6, so actually a sample size of 5, sorry, 2, 3, 4, 5. Sample size of 5, we looked at the critical value for that, and it was greater than 0.591, so this is not significant. Use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. In other words, you don't want to do too much extrapolation. You want to use predictions only for values within the data set, and I'll explain this when we go through our second example. If the regression equation does not appear to be useful, then the best we can do is to use the sample mean, and that's what we have going on in this case. The average for the height is 177.3. So the best that we can do in this case, because we found that our correlation coefficient was not strong enough, the best we can do is to simply use the average of 177.3 as our predicted height for an individual whose shoe size is in this neighborhood. Okay, well, that's not very exciting. And so what we can do is we can go further and use a better data set that actually gives us some significant results. If we go ahead and use a much larger data set, in this case we've got 40 shoe prints, and they're paired with the heights of the individuals that produced those shoe prints. If we use the 40 pairs of shoe print lengths and the paired heights of the person, we find that the correlation coefficient is 0.813 using the correlation function in Excel. If we go back to table A6, which you can see in PowerPoint 10-2, you'll see that in this case, the correlation is strong enough to be significant. So the regression line is going to fit the points reasonably well. Well, let's jump into Excel and work through all of this. I'm going to take us back to slide number 5 because I want to use these equations here when working with these shoe print lengths and the heights. All right, let me just take up the whole screen for a minute here. With this data, let's take a look and see what the scatter plot looks like. Insert scatter plot. Whoa, that is not too exciting. Let's expand that out. That's just way too clustered. Goodness. I could play with this, but I just wanted to look at this. All right, if you see that, all of this data is kind of lined up in a little bit better of a fashion than what we saw with our 5 shoe prints and 5 heights. All right, it looks pretty good. If we can find a line that goes right through the middle there, that would be a pretty good estimate for the relationship between the shoe print and the height. All right, let's just clear that out of there. Bring this back down to size. If we're going to calculate this, remember we got to find the correlation coefficient. We need to find the standard deviation for both of those. We also need to find, man, if I could just type tonight. We're also going to need to find the average of each of those columns. All right. Equals CORREL. Here's our first array of data, comma, our second array of data, close the parentheses. We have a correlation coefficient with this data of 0.812948. If you go back to table A6 and 10-2, you'll see that that is greater than the critical value with a sample size of 40. But we're good to go. The standard deviation for each of these, let's calculate that. STDEV.S, it's a sample standard deviation for the shoe prints. And we want to do the same thing for sample standard deviation of the heights. Get that. And then we want to find the average length of the shoe print. That's going to be just the average of the shoe print data. And we also want to do the same thing, copy that formula over to cell here. And that's the average height in this data. Okay. All right, let's find the slope. The slope for all of this is going to be equal to the correlation coefficient, that, times the standard deviation of the height, and divided by the standard deviation of the shoe. Hit enter. So we've got a slope of 3.2, and the intercept, y-intercept, is going to be the average. Let me give myself a label here. The intercept is going to be equal to the average y value minus the slope times the average width, the shoe print length, and hit return on that, and you get 80.93. Okay, 3.21 is the slope, and 80.93 is the intercept. Now back over here, you have 80.9 as the intercept plus 3.22. 3.22x is the slope. Awesome. Using Excel, we got the right numbers. There's our slope, and here's the intercept. So remember these equations here for the slope and the intercept of your regression line. So you can see that that's the picture of the line. You got your dot plot there. Here's the equation, 80.9 plus 3.22x. Now we can use the regression equation to estimate the height of an individual with a shoe print length of 29 centimeters. 29 centimeters is in the, oops, if we go over here, you can see that 29 centimeters is right in the range of the values here. What I said earlier, it would not be correct to use this equation if we were trying to predict the height of an individual with a shoe print that was 5 centimeters, or if we were trying to predict the height of an individual with a shoe print that was 45. Those are outside of the range of the data. But using this equation, it makes sense that we could estimate the height of an individual that gave us a shoe print of 29 centimeters, because that's right in the range, right in the neighborhood of the numbers in our data set. So we have the intercept of 80.9, slope of 3.22, substitute 29 in for x, and a person with a shoe length of 29 centimeters, you can expect them to be about 174.3 centimeters tall. Okay, so get some practice with, whoops, get some practice with using these equations to find the slope and the intercept, which gives you the equation of the regression line. Equations like this right here, where you have the intercept and the slope, and then you can use the equation, whoop, totally dropped out of that one. You can use the equation for some pretty decent prediction, just like we did here at the end. Okay, there you go, 10-3 regression.